Welcome back. Let's do a few last examples. Okay, for this example, we're rolling a six-sided die 4 times, and we're noticing the sequence of numbers. So when I say sequence, then that means the order that we see these things matters, because rolling a 1 and a 2 and a 3 and a 4 is different than rolling a 4 followed by a 3 followed by a 2 followed by a 1. Those would be different sequences. So I should be thinking maybe factorials might be involved, maybe the multiplication principle. If I'm thinking about the sample space, multiplication principle will do that for me right away, because for each of the 4 rolls, we have 6 options. 6 options for the first roll, 6 for the second, 6 for the third, and 6 for the fourth. So 6 to the power of 4. For part A, we want 4 different numbers, and if we wanted them to be all different, that means that we would need 4 different numbers in some kind of an order. And again, we should be thinking about a permutation here. This is really us taking out of the 6 numbers that are possible, selecting 4 of them, and then putting them in some kind of an order. That would give you 4 different numbers in all the different arrangements. So the probability for us to get all things different, so all 4 numbers to be different, should just be P64 divided by 6 to the power of 4, and that's around 27-ish percent, 0.2778. Okay, so we've tackled our first problem, the first problem of us having 4 numbers ruled that are all different from each other. What about in part B if we roll a 5 exactly twice? So, if we're thinking back to the question about the passwords that we did, there was something similar about having 2 Q's show up in your password. This is the same kind of an idea, because if we're thinking about how I've got 4 different roles, and if I wanted to have exactly 2 5s, then I would need to first decide out of those 4 different roles that we have, which ones are going to be the 5s. So out of the 4 roles, choose 2 of them to have 5s in them. So I might say this is going to be a 5 and that one's going to be a 5. So now I know what those roles are going to be, and I need to decide what the other 2 roles are. And they could be anything as long as it's not a 5. So I would have 5 choices for the one remaining role and 5 choices for the other remaining role. So I would have 4C2 times a 5 times another 5, or 4C2 times 5 squared. Choosing where the 5s go, and then for the 2 remaining places, put in anything that isn't a 5. So that means that the probability of us rolling exactly 2 5s should be 4C2 times 5 squared over 6 to the power of 4, which is about 0.1157. Okay, another example. Bella is having a dinner party, 8 guests, so not including Bella. She's not one of the 8. So really there's 9 people at the party, Bella plus her 8 guests. The question is all about inviting guests at random. She has 16 friends to choose from. 2 of those friends are Edward and Jacob. So the question that we have is, what are the probabilities of various people showing up to this party or being invited to this party? First, for the sample space, that's a quick one for us to calculate, because the sample space usually is. All we're doing is selecting people to come to a party. So this is kind of similar to the previous question where we were selecting people with hats to come on a field trip to the cafeteria. We're not really caring about what order I pick these people in. They're not filling in particular roles. They don't have special positions that they're being selected for. It's just who's coming to the party. So out of the 16 friends, we are going to select 8 of them, 16C8. That should be the number of ways to select 8 people out of 16 to come to the party. And now, let's figure out for this question, part A, what's the probability that Edward will be one of those 8 people that are invited? So, number of ways that I can select Edward. First off, well, first there's one Edward, and there's 1C1 ways to select Edward. So there we go, we've got one person at the party, it's going to be Edward. That means I need to select 7 other people, and I need to select them from the 15 other friends that Bella has. So 15C7, that should be our other way. So there's one Edward, I select him, and then there's 15 other people, and I need to select 7 of them. So the probability that I'll select Edward should be 1C1, 15C7 over 16C8. Which actually, interestingly enough, turns out to be equal to a half. Sometimes we wind up with particularly nice numbers that are just a fluke. Just as a little side note, there will be some people who will misinterpret this or think that the reason for the half is there is for a reason that's not true. So there's probably somebody right now watching this video thinking that it's a half because either Edward will be invited or he won't, and there's 2 options, so 50-50. Unfortunately, this half is just a fluke. If we'd had different numbers of friends for Bella or were inviting different numbers of people to the party, the probability of Edward being invited wouldn't be a half. In this case, the 1/2 is just a fluke that turns out because of the result of the particular numbers that we're working with. So it's not because Edward either is invited or he's not. It's just by chance that the 1/2 turned out to be our answer here. Okay, what about part B? Part B, we want Edward and Jacob to be invited. And so, same kind of an idea here. I'm going to say, well, if we're inviting Edward and Jacob, then there'd be 2 people. There's an Edward and a Jacob, and I want to make sure that I invite them both. So those 2 special people have been invited. And then there's 14 other friends still left to choose from, and I need 6 of them for this party to come to make my group of 8. So the probability of us getting Edward and Jacob both to this party just by chance should be 2C2, 14C6 out of 16C8. And then now we just need to compute that, and that's about 0.2333. Just as a little side note before I move on to the next, the 1C1 and the 2C2, I wrote those down just sort of for my own thinking, but of course those are both equal to 1. 1C1 is just equal to 1 and 2C2 is just equal to 1, so do you really need to have them in your answer? Not really. We could have just said, well, if Edward's invited, then there would be 15 people and we need 7 of them. If Edward and Jacob were invited, we would have 14 people and we would need 6 of them. So we don't really need to write in the 2C2 or the 1C1. Okay, part C. At least one of Edward and Jacob will be invited. So when I say at least one of Edward and Jacob, I could say as far as probability goes, that would mean looking for Edward or Jacob or both. In fact, I'm looking for E union J, essentially. I want Edward or Jacob or both to be invited. And there's 2 ways that I could tackle this. So one way would be using inclusion-exclusion. I could say, well, if we look for Edward or Jacob to be invited, we would find the probability that Edward is invited, add on to it the probability that Jacob is invited, and then remove the probability that they're both invited, that Edward and Jacob are invited. And conveniently enough, we kind of have enough information now to solve this problem, because we found out before that the probability that Edward would be invited turns out to just be 15C7 out of 16C8. And we could reason for the same reason why for Edward it's 15C7 out of 16C8. It should be the same thing for Jacob, because if we were looking for the probability of Jacob to be invited, if Jacob were coming to the party, then there would be 15 other friends, and we would have to invite 7 of those other friends to join Jacob to make our group of 8. And we also figured out in the previous part B, Edward and Jacob both showing up to the party. That should be 14C6 out of 16C8. And that gives us our answer of about 0.77, or sorry, 7667. So just almost 77%. Another way that we could have tackled this, so one way was inclusion exclusion. Another way would be by using the complement, because we're looking for Edward or Jacob or both to be invited to the party. And I could say, well, the opposite of that is that Edward is not invited and Jacob's not invited. So the opposite of Edward or Jacob or both being there would be not Edward and also not Jacob. And if we're thinking about that, if we didn't want to invite Jacob and we didn't want to invite Edward, then that means out of the 14 other friends, the 8 people coming to the party would come from those 14. We would say, sorry, Jacob, sorry, Edward, you're not coming to this party. So, Bella, you've only really got 14 friends to choose from. Choose your 8 friends from those 14 out of that sample space of 16C8. And this gives you exactly the same answer as the previous. It gives you exactly the same 0.7667. It's just a question of which do you think is easier for you to compute. I think both of them are equally easy. So if you thought about that you already had enough information to use inclusion exclusion, then the first way is great. If you didn't and you thought about using the complement, that also works equally well. Okay, one last problem, and this one's a classic. This one's called the birthday problem. And for this one, you have a group of people and you're wondering what's the probability that 2 or more people in that group have the same birthday. There is one assumption that we're going to have to make here, and this is maybe not necessarily a true assumption to make, and it probably isn't if we look at data for actual birth dates, but we're going to have to assume that all 365 days are equally likely. So by that I mean when I select a person at random out in the world, the probability that person is born on a particular day, 1 out of 365. That's probably not necessarily true. So first obvious reason, there's not always 365 days in the year, so we're ignoring people who are born on the leap year, on a leap day. But there's also more parts of the year that are more likely to have babies than others. So every day of the year is not equally likely for people to be born on it. But let's pretend that it is. Let's pretend that it's close enough to be equally likely for us to solve this problem. If that's the case, if we have a group of 10 people, and if we're thinking about the sample space would be, well, the first person has 365 days to be born on, and so does the second person, and so does the third person, all the way up to the very last person. So, in other words, you'd have 10 of these 365s multiplied together. And I'm thinking about this again, at least 2 people having the same birthday. There are lots of different scenarios there. I'm going to think about using the complement. And to use the complement, so probability of at least 2 with the same birthday would be 1 minus nobody has the same birthday, or in other words, all different birthdays. And all different birthdays, that's easy enough for us to do because there's 365 days. I'm going to need 10 of them, and they need to be in some kind of an order for those 10 people. So kind of like permutations from before that we used when we were looking at a password where all the digits were different, or when we rolled the dice 4 times and we were looking for all the rolls to be different. Similarly here, for selecting 10 birthdays and having 10 birthdays to be different, it should be P365 10, because we need 10 birthdays on 10 different days and then put them in some sort of an order that those 10 people are in. So P365 10 out of 365 to the power of 10. And when I compute it, not a big surprise, this is not very big. So for 10 people, the chances of us having somebody with the same birthday as somebody else, only around 11-ish percent, 0.1169. But if we decided to repeat this and say, well, what if we did this with a group of 36 people instead of 10 people? It would be a similar sort of thinking. Again, I would say, well, you want at least 2 people to have the same birthday. So that would be 1 minus everybody's all different. You'd say, well, for the sample space, instead of 10 people each having 365 options, it would be 36 people each with 365 options. So our sample space should be 365 multiplied by itself 36 times. And then for the numerator, for everything to be different, we don't just need 10 different birthdays, we need 36 birthdays. So P 365, 36. And this turns out to be a lot higher. In fact, with only 36 people in the room, the chance of you having 2 or more people sharing a birthday, kind of surprisingly enough, it's actually pretty big, 0.8322. Now, you may wonder, why did I stop at 36 people? I did that because, unfortunately, our calculator sort of taps out here. If you tried to do this with 40 people or more, your calculator will give you an error. And the reason it's giving you an error is because 365 to the power of 40 is just too big, as is P36540. It's also way too big for our calculator to compute. But using a computer rather than a calculator, I was able to figure out, well, what happens if you had 40 people or 50 or 60. So just as a little aside here, if you had 50 people, the probability turns out to be 97% that you will have 2 or more people with the same birthday. And if you had 60 people in the same room, which is not that big of a group, the probability for that, for you to have 60 people, to have 2 or more people with the same birthday, is above 99%. It's 0.9941. So this is sort of the counterintuitive birthday problem, that even though there's 365 days in a year, you don't really need that many people. Even with only 36 people, the chances are very good that you are going to have 2 or more people with the same birthday. And that if we wanted a high probability, just 50 people is good enough. For 50 people, you're at a 97% chance that you will have 2 or more people with the same birthday.